There are other ways besides the ones I showed you for making decisions. And they are based on what they are called the learning machines. These are something that I believed in. They are very useful, I think, but they are not much taught in university courses. So that's the reason why they are here. And because learning anyway, no matter if you use this machine for classifying or not, you need learning for enabling cognitivity. So sooner or later, something like this will become extremely important. So far, someone is tackling it, someone not. They provide theoretical frameworks, they provide basic applications, but it's becoming important, really important. But what does learning mean? Let's start from the basic again. To gain knowledge or understanding of or skill by study, instruction, or experience. Study, instruction, experience. So, basically, we can gain knowledge by receiving information in a structured way, for example, studying, or by experiencing the information in itself. Which means that we go out, we see the things, we make mistakes, and then, sooner or later, hopefully if we are smart, we learn from our mistakes. Machine learning translates this one into offline learning, which basically is supervised training or unsupervised training, or online learning. These are the main branches that we will discuss about briefly, and that basically enable the full cognitivity of the system. So we have supervised learning or unsupervised learning. These come handy in different situations. But nevertheless, in both cases, we have the control of the information that we feed to the machine for learning. Supervised is when we really tell the machine, look, this is the information and this is what you need to decide. Unsupervised is when you feed the machine the information and the machine processes it by its own, and then only afterwards, that it has been fully processed, we can apply something and make it available for us in the proper way. And this is, for example, the case of clustering. If you have very complex domains that you want to see, or very complex patterns, it's possible to recover these patterns which are inherent in the information simply by clustering, by providing the information to the machine, and the machine does the work for you. That happens, for example, let me give you a very stupid example. Have you ever tried to put some transparent color in PowerPoint with just by clicking? No. Have you ever used Photoshop? Someone? Paint? Paint. Okay, paint. Let's say paint. Do you know that in Paint there is this magic wand that you click and it selects the area with similar color? That's clustering. You provide a SID, you provide the sensitivity of the algorithm, poof, and it gets clustered. Same happens here. You provide information, you provide a basic thing, you provide a SID, and voila. The patterns are coming out. I will show you an application later on. When we talk about supervised learning, the very basic are the neural networks. How many of you have ever heard about it? Okay, a number. How many of you have ever used it? 2, okay. How many of you is aware that you own, for sure, a neural network? You know why? Tell me. Sorry? Smartphones? No way. The brain, no way, I'm talking about machines, about technology. All of you own a neural network at least. Do you have laptops? Yes. Do you know how the touchpad works? It's a neural network. The biggest producer, I mean, the only one who has the patent, basically, is a company called Synaptics. So you deal with the neural networks every day, but you don't know it. Because they are hidden somehow. But they are extremely powerful. Otherwise, there are other techniques called support vector machines, for example. We will see both of them. But let's start from the neural networks. They are an extremely old concept. There is this nice book from Simon Eiking about neural networks, Comprehensive Foundation, where you can find basically everything. And this started because in the 60s, they started taking squids, opening the squids, and analyzing the brain of the squids. Wow, well, disgusting. But why squids? Because they have one neuron. So they have one extremely big neuron that they could dissect, analyze, use electricity on it, and see what was going on. What they discovered is that given the inputs you could give to the neuron, you could have a kind of binary response somehow. And this binary response is given by an activation function. The same type of functionality that you have in your neurons, for example. Or in other, for example, there are, in the vision system of the brain, cells which have, neurons which have different activation functions. They are called, for example, center on or center off. Meaning that if there is a hitting in the center of the function, not of the neuron, basically where the function is centered, you have a positive response. Another where you have a positive response only at the edge of the domain of the function. That's a basic example. You define the neural networks that you use also according to the activation function that you use. The most simple one is the sigmoid. You use a sigmoid function. You can use a zero-centered sigmoid function, so it has positive and negative response. You can have just a positive sigmoid function, or you can have, for example, a Gaussian, which is the case of the radial basis function, because they are radial in the domain. And you simply take the inputs, you apply a weight to them, to somehow normalize, compare them, and so on. Sum them, pass to the function, and then you have an output. That's the simplest neuron you have. You don't have billions of outputs in one neuron, you have one. That's the basic building block of neural networks. But we can do more if we start putting neurons together. We want a brain, so let's put more neurons. And how we do it? This way. For example, this one is called a feed-forward neural network because the information flows just in one direction. We can have neural networks with internal or external feedbacks. And we have, that's called multi-layer perceptron. Again, old, very old. It's the second neural network that happened after the single neuron. Where you have an input layer, hidden layers that basically perform the processing, and you have the output layer that defines the output. Usually, rule of thumb for each of the domain, that each of the axes of the domain you are trying to have as output, you put one output neuron. Rule of thumb. All of this it goes for rule of thumb. the correct structure of the neural network you use for your application, good luck finding it. You need to, it's a trial and error process. There are smarter ways, I will tell you in a while how to do it. But the important thing for learning is how we train it. Because these guys here, they come out from your MATLAB tool completely dumb. You can generate a simple neural network in MATLAB. It's one command line. But what does it do as soon as you generate it? Nothing. It gives you wrong answers. Because it's poor baby, it was just born. It has no clue about how the world is. So you need to tell the neural network how the world is. How you do it? With a technique called backpropagation. Because you present your data set. Data set is basically the features that you have already classified. So you need to know beforehand which is the outcome of the data you present to the neural network. And then you present the data set to the neural network, you give the correct answer to the neural network, and then you start adjusting the weights of the neural network starting from the output layer and back to the input layer. That's why it's called backpropagation. And it's done mathematically by optimizing a descending gradient. There are two ways of doing this type of training. What's called a batch, which means that I give you all the data I have for training, I give you all the answer, and when we have, at the end, all the answer and the average and so on, and then I train the network. So I find a global compromise. Or I can do something incremental. I give you one example about how the world is, and then you retrain. And then I give you the following example, and then you retrain. And you do like this until it's done. And this, it's done, it can, of course, be defined two ways. The simplest one is that stop after a certain number of epochs. An epoch means that I have presented the entire batch of data once, one epoch. Or because my error function that I need to define for the backpropagation is below a certain threshold that I decide. Simplest way. I am not entering into more details than this one because you take MATLAB and you use it because it's fair. Two command lines and you have your neural network. There is also a very nice graphical user interface. Supervector machines. These ones are very, very powerful tools. More powerful than the neural networks, but they are less, known. They are considered the neural networks for geeks, basically. They are also linear classifiers. Also, a neural network is a linear classifier. But linear classifier means that I have, for example, two classes, and I define a hyperplane between the two classes. Which hyperplane? The best one that ensures me the highest decision probability and the minimum error possible. In the supervector machine world, you define a good hyperplane as the one that provides you the maximum margin, which means the one that grants you the highest decision robustness, maximum margin. This is the basic concept. This is the book that I would suggest you if you are interested in. It's the Christianini Show Taylor. That's basically considered the Bible of the supervector machines. But why it's called supervector machines? Someone thinks that they are called supervector machines because they are machines that support vectors. Wrong. They are machines that are based on support vectors. What is a support vector? A support vector is the sample of the data set the samples of the data set which are closer to the decision hyperplane. And that could be used for defining the decision hyperplane. This has a huge, huge advantage. In the neural networks, if you want to have a very good decision, you need to probably process a bit more the data. And this means that if you have, big feature space, wide feature space, in the sense that you have wide dimension of the feature space, it takes a lot of sums, a lot of multiplications in order to process the data. If you increase the number of neurons, even more. In this case, this machine is called a kernel machine because you define the kernel of the decision space. And this kernel of the decision space is basically composed just by the support vector. So you can have huge training sets with millions of samples in very widely dimensional feature space, but you can have in the end 3 or 4 support vectors. And you make a linear decision based on this support vector, which are only 3 or 4. Which means that you have a very reduced number of sums and multiplications. See, why no one is using it? Is it so powerful? Because there is a drawback. You pay this reduced online complexity in the training process, because you need to extract the kernel of the space, which means that you need to define the auto vectors and the auto values of the kernel. A huge number of sum and multiplications. But if you do it offline, maybe we have to gain out of it.